Okay, so just a heads up that we are recording. So if you don't want your face or anything to appear on the recording, just mute your video or something like that. Um, and so I'd like to thank all of you for coming to our last colloquium of the semester. And not that I haven't enjoyed these, but perhaps the last of our regularly scheduled virtual colloquia. And so today we have Jerry Tuttle speaking. He is a retired insurance company actuary. He worked for various insurance companies in New York and New Jersey, most recently with Renaissance Reinsurance in New York City as Senior Vice President and Senior Pricing Actuary. He holds the insurance designations of Fellow of the Casualty Actuarial Society and Chartered Property Casualty Underwriter. Jerry is currently an adjunct online instructor at Rocky Mountain College of Art and Design, teaching math to art students. He holds a master's in math from the University of Virginia, a master's in educational technology from New Jersey City University, and he is half a course away from a master's in data analytics at Southern New Hampshire University. Jerry spoke to this group last year, actually, and some of you may have attended that, on actuaries and data science. And he returns today to share some applications of data science using the passenger list of the Titanic. And so I will turn it over now. And if you weren't here right when I asked the question earlier, if you have questions, go ahead, put them in the chat. I will be monitoring that, and I'll try to find an opportune moment to ask it if you have a question. So I will quiet myself now and let Jerry start talking.
Okay, thank you very much. I'm not on the video right now, but if I were, you would see that I'm proudly wearing my FGCU Actuarial Science t-shirt, which I got a couple of years ago. And at the end of this talk, I'd like to talk about the Actuarial Club again. But this talk is about data science. And data science is all around us. You can't buy anything on the internet and sometimes even in person without the vendor keeping track of your purchases and making suggestions for what you might want to buy in the future. And that comes from data science. There's actually 2 help wanted ads locally right now from 2 really big organizations. One is a very big hospital. One is a very big auto rental company. They're looking for data scientists. This is a graphic from one of my students at an art school. This is Jack and Leo. If you saw the movie, perhaps you can picture the scene. And we're going to talk about a couple of applications in data science using the Titanic passenger list as our data set. So first, briefly about the Titanic. This was a British luxury ship that sank on its maiden voyage in 1912. There were 2,000 plus passengers and crew, and 1,500 or so died. You'd think something like the number of deaths would be a pretty undisputable number, but the counts differ by source. And some names on the passenger list canceled and never took the voyage. Some people traveled under aliases and were counted twice. I'm not sure why you would do that, but that seems to have been the case. Some people were rescued soon and then died soon after, so there's a question of how do you count them. Probably many of us have seen the 1997 movie with Leonardo DiCaprio and Kate Winslet. I'd forgotten how many years ago that was. That's 20 plus years ago. That movie was a sequel to a 1953 movie with Barbara Stanwyck. And the passenger list of the Titanic is a very popular data set for various kinds of data analysis. This is not what the 2 main characters looked like in 1997. This is more current. But if you saw the movie, a very handsome Leonardo DiCaprio played Jack Dawson at age 20. And he had a 3rd-class ticket and was traveling with a male friend. And a very beautiful Kate Winslet played Rose DeWitt Bukater, who in the movie played a 17-year-old person. She had a first-class ticket and was traveling with her mother. Does anyone know how Dawson got his ship ticket? Someone like to call out? I'll listen for the answer. Okay, hearing no answers, I'll move on. Jack Dawson was in a card game, and he won the ticket in a card game right before.
Yes, Katie Johnson put that in the chat just as you said it.
Right before the ship took off, he won the ticket, and so certainly he would not be in the passenger list because that happened right before. Why was Kate not on the passenger list? Anyone know the answer to that? Well, the answer is that both characters are fictional. They're not on the passenger list. They're fictional characters. Other people in the movie did play real passengers, but the two of them did not. So as I looked at this data set, one of the first things I wondered is what did the data say, particularly about the Leonardo DiCaprio character? But they're both fictional characters. So let me back up a little bit and ask, what is data science? It's a fairly new field, and it's not well defined. Although if I ask what is mathematics, I don't think I get a single answer to that either. But one of the popular explanations is it's the Venn diagram intersection among programming, computer science, math, statistics, and then subject matter knowledge. Data science is the intersection of those three. And the goal is to extract meaningful insights from data, translating into tangible business value. So it's generally a very applied subject. There are theoretical data scientists, but really the goal is to get some tangible business value out of the analysis. And here's one diagram of the data science process. So there's data in the middle. You need both a business understanding of the data and then a more technical understanding of the data. The business understanding, I've sort of given you a little background on that. Then you prepare the data, and data is invariably dirty. We'll talk about that a little bit. Then you create a model and evaluate it, and then you put the model into production. And I thought about this. Hopefully a number of the faculty has a copy of Polya's How to Solve It, Techniques on Solving Math Problems. And I'm not sure that that's really terribly different than this process here. So what is our goal? So we have the data set of the Titanic passengers, including various features about them. And even the data set of the passengers is not unique. There are a few different versions of them. I'm using the Kaggle version. Kaggle is yet one more subsidiary of Google. And we want to develop a data science model that will predict whether any particular passenger will survive. There are many possible data science techniques. I'm going to limit this discussion to just two of them, decision trees and regression. And again, let me digress a minute. As an actuary, actuaries can consider ourselves among the earliest data scientists. The things actuaries do are very similar to the things data scientists do, just the techniques are different. And one of the similarities is that in much actuarial work, we're trying to make forecasts of very random and unknown things, and we use more than one technique. And we hope we'll learn something from the different techniques, and that the techniques will converge. They may or may not. But that's something I have not seen in many of my math and statistics classes. Generally, you're asked to do a problem, you do it one way and you're done. In data science, you often will use several techniques and see how they compare. So now let's talk about the data set. The data set had a few more variables before, greater than 9. I'm only going to use 9 of them. The dependent variable is survival. Either a person survived or they didn't. 0 for no, 1 for yes. There's the passenger ticket class, first, second, or third. There's sex, just male or female. Remember, this is 1912. Sometimes there are more categories nowadays. Age in years, number of siblings and spouses aboard, number of parents and children aboard, ticket number, passenger fare, cabin number, and port of embarkation. Remember, this is a British luxury ship. It actually departed from 3 different cities. I forget the name of the cities, but they're abbreviated C, Q, and S, and they're not cities that I'm actually familiar with from the UK. There are a few more things in the data set. There's ID and passenger name. I didn't think those were particularly interesting, so I ignored them. One of the things that's always done in data science is you don't use all your data. You randomly select, say, 80% of it to train your model, and then 20% of it to test it. So here this is not the Titanic data, but I've randomly taken 80% of the data, which I'm calling the blue squares, and I'm fitting a regression line to the training data. But then when I want to ask how good is the straight line, I don't ask about it with the training data. I ask about it with the data that the regression hasn't seen, and that's the testing data, and that's the red data. So I always test my models on the data it hasn't seen. That's also something I have not experienced in my statistics classes. Maybe statistics has changed, but this is something somewhat unique, I think, to data science. And the result of not doing this is sometimes overfitting your model. You can perfectly fit your model on training data and then discover it doesn't fit the testing data at all. Next, we need to talk about how are we going to measure how well our model has performed. And particularly in this case where we have a binomial dependent variable survival, yes or no. The actual state is either yes or no, and the prediction of any data point is either yes or no. So this 2x2 matrix is called a confusion matrix. So there are 4 states, 2 actuals and 2 predicteds. And certainly this is very common in statistics. But this pregnancy thing, I think, is an interesting analogy for how to figure out what goes in what box. If the pregnancy test is positive to a male, the doctor tells the male he's pregnant. And of course, that's a false negative. If the pregnancy test is negative to a woman who's obviously pregnant, that's a false negative. And having seen this, I will not forget what goes into the false positive, false negative boxes in the future. But more seriously, this matrix gives us 3 possibilities in assessing performance measure. You can go down the main diagonal and calculate the sum of these compared to all your data items and say that's accuracy. True negative plus true positive divided by a number of items is, as a percentage, how accurate your prediction is. You can look at the true negative plus true positive plus false negative. you could look at the second row, take the sum of these as your denominator compared to the true positives. That's the true positive rate. What percent of true positives are all your actual yeses? Or you can go down the second column and ask what percent is your true positives of all the positive predictions. So these are three potential ways to measure performance. There are others. Another one is taking true positives versus false positives and graphing them over a variety of probability thresholds and calculating the area under that curve. We'll talk a little bit about that if there's time at the end. So now I'm going to talk generally about the two models I'm going to use. I'm going to use a decision tree, and I'm going to use logistic regression. So first, what is a decision tree? There are many decision trees we come across in math. This is a different one. This is not the tree that enumerates the various probabilities of, say, how many ways can you get 2 boys out of 5 children. Nor is it the decision tree that gives you a number of possible outcomes, asks you to compute the expected value of each outcome, and then you go back and choose which path gives you the best decision. Those are also decision trees. That's not this one. The decision tree we're going to use is one that predicts the value of the dependent variable by successively splitting the variables into subsets. We're going to start at something called the root node, and we're going to continue making these partitions until further splits no longer add any value. The algorithm tests each variable for each possible split, and so just thinking about that for a moment, you can see that this can be potentially a computer-intensive task, and it's the sort of thing that certainly could have been done manually in the pre-computer era, or in the era where you didn't have a whole lot of RAM, but obviously that would be pretty time-consuming. Today we certainly have plenty of RAM to do this, and this is one of these kind of brute force algorithms that data science loves to do. So at each node, we split one variable, and then we move forward, which is down the tree, never backwards. And there are various measures of how we define what's the best way to do the split. Generally, you're trying to get as homogeneous a grouping of the target variable within the subsets. And this is one formula to do it, called the Gini ratio. Here is a very simple decision tree. We haven't gotten to the Titanic yet. Here's a 7 observation data set. There's only 3 variables, and this is an automobile collision. So in collisions, there may or may not be a rear end collision. There may or may not be a driver or passenger experiencing whiplash, and there may or may not have been fraud in this whole collision. And of course, as actuaries and insurance people, we're very interested in fraud and not paying for fraud. So this is a very simplified data set. And I ran this through the decision tree model. So this starts at the beginning with all the data. And the algorithm decided the best split was splitting with rear end and not whiplash. And splitting with rear end, which is either a yes or a no. If the rear end is false, which is a 0, that takes you down this path. Rear ends of false are 71% of the data. That's 1, 2, 3, 4, 5 sevenths. And within, I'm sorry, it's these 1, 2, 3, 4, 5. I assume you see my arrow? I'm not sure. If rear ends are false, then of those that are false, 80% of those are not fraudulent and 20% are fraud. If rear ends are true, 100% of them are frauds. So now for any observation, we can run it through this model, and this gives you a prediction of whether that particular combination is or is not fraudulent. And the interesting thing is that the tree chose rear end as the better way to split the data than whiplash. It could have chosen whiplash, but that would have gotten you a less homogeneous result. Now let's talk briefly about regression. I suspect in this audience, everyone knows something about linear regression. Probably in this audience, many people know a lot about linear regression. Probably many people know a lot more than I do. In linear regression, you have n independent variables, and you're fitting a linear model with coefficients, the betas, equaling some dependent variable y. There are a number of important assumptions of linear regression. In statistics class to liberal arts students, maybe you ignore those assumptions. Certainly in a more mathematical class, those assumptions are more important. But the one that's important in this context is the dependent variable, which for us is survival, has to be continuous. Our dependent variable has two values, 0 and 1. It's not continuous. And linear regression would fit a continuous linear expression, and the expression would go below 0 and past 1. So linear regression is not an appropriate tool for something like this where we have a categorical dependent variable. So this takes us to logistic regression. In logistic regression, we again have the n independent variables, and we still want to fit this sort of linear expression. But this time, we're going to raise it to the e, add 1, put it in the denominator with 1 in the numerator, and set that equal to p. P is now the probability that y equals 1. And when we do that, now we have a curve between 0 and 1. And with a little algebra, you probably remember that odds, what are the odds of something happening, are p over 1 minus p. And if you take the natural log of odds, you get a really nice algebraic relationship. The odds ratio is the ratio now that y equals 1, which is what we're interested in. Y equals 1 being survival. And generally, when we do these calculations, we do need to set some sort of threshold on probabilities. Commonly, we initially set the threshold at 0.5. And we say if the regression predicts a value greater than 0.5, we're going to call that a y equals 1, which here is survival, otherwise y equals 0. And we can vary that. So that's quickly logistic regression. Now let's spend some time with the Titanic data. The first thing one normally does is we look at what kind of data we have. Some of the data is numeric, and some of the data is not numeric. Within the data that's not numeric, some of it are factors. Factors have levels, such as the fare, F-A-R-E, of the passenger, being a first-class passenger, second class, third class. Those are categorical, but those are factors. Second class means something not as good as first class. So we want to know what are factors and do they have levels. We're going to create some summaries and plots, distributions, outliers, missing data, duplicate records. And the first thing I noticed is we have a lot of missing data and or blank data. And what are we going to do with them? And let me digress just a minute. For all the math and statistics and actuarial classes I've had, I don't recall anything with data that was blank or missing or anything. And that's something to think about as teachers. I'd like to propose, whatever your class is you're teaching, present a problem that's missing some data deliberately, and let the students worry about that. What are you going to do about it? I think you'll get some interesting responses. So I had that issue with the Titanic data, starting with age. I had 263 not available age observations. I had one blank for fare. I had nearly half blank for cabin, and I had 2 blank for city of embarkation. So what are you going to do with this? In theory, you could go back to the person who prepared the data. But remember, this is 1912 data. That person's long gone. That's not going to work. You can delete an observation. You can delete the entire column. Or you can impute a value. Impute is a nice way of saying make it up. Does anyone have any thoughts on any of this? I'll accept questions right now or suggestions.
Well, as the moderator, I'll jump in if no one else has any thoughts. I haven't seen anything in the chat yet, but I mean, my first thought is that something like fare, if you're only missing one blank, right? I don't feel as bad deleting like one entry, right? But with something like cabin, missing 1,000 of them, it seems kind of more problematic to delete all those entries. Those are kind of my thoughts that I see.
Okay.
I have a suggestion to get rid of missing parameters, like cabin, delete.
Yes, and in fact, that's what I did. I deleted the whole column of cabin. I decided there were just too many to try to impute, and it didn't really seem that important to me.
And then we've got a guess or a comment in the chat. Someone said, for variables like age, could you compute the mean of the information we have to estimate for the missing data?
Yeah, and I'll get to that. So cabin, I did delete the entire column. This is a very common data set. Many people have played with it, and people have done different things with it, and people have tried to do things with cabin. I think they tried to relate cabin with fare. I chose not to do that. So I did delete cabin altogether. For the embarkation and the fare, I chose the mode. I didn't think that would be too terrible. Age seems like an important variable. It seems too many to delete 263 observations. I used the mean of all the other ages, and I said all those not available ages I'm going to set to that mean. That's also a controversial choice. There are other things you could have done. You could have asked, you know, are there other people with the same name with that age, and could you do something with that? There are other things you could do, but that's what I chose to do. I calculated the mean of all the others, and I set these missing ones equal to that. But the point is, you have to do something. You can't ask the teacher for help. You can't do nothing. And that's also very similar to actuarial work. Your data is often incomplete, and you're not going to get a complete answer. You got to do something, and it may or may not be the right thing, but you got to do something. Next, I created some charts. R is even better than Excel at computing charts. I computed an age distribution. But now this age is highly influenced by the fact that 263 of them have the same value. So there's some distortion there. But excluding that, you can get some idea of the skewness of that. Certainly the fares, most people wrote lower fares or fewer higher fares. $300 sounds like a lot of money in 1912. Parts, remember, is number of parents or children aboard. SIBS is number of siblings or spouses aboard. I computed correlation of my numeric variables. These are nicely color-coded, which doesn't help. Whoops, I don't want to do that. It doesn't help me because I'm color challenged, but nevertheless, it gives me the numbers. It does give me low correlations among pairs of variables. That's important in regression. So that's good for regression purposes. These are some multivariate data plots. Now I'm graphing both the died versus survived variable versus one of these other variables. So this is by gender of the survivors. I'm sorry, of the people that died. A lot more of the percentage of males died, a lot more of the percentage of females survived, by gender within ticket class, by age, although again I've got that distortion of the mean, and by fare. Not surprisingly, there's a lot of people at the lowest fare end who didn't survive. If you saw the movie, you might sort of remember why that is. We'll move on from there. But this gives us some idea of what the data looks like in graphical form. Decision trees are non-parametric, which is nice. But there are a few things not so nice about them, and one of them is that they're greedy. And what does greedy mean? Greedy means they make a decision based on the current node, but they can't look ahead for a better decision. And it took me a long time to get a good example of that, but here's the example I found. Suppose you have a fictitious currency system, and you need to make change for 30 cents from a dollar using the fewest number of coins. And the coins you have are 25-cent coins, 15-cent coins, and 1-cent coins. So you're making change for 30 cents. You'd start with 25 cents because that leaves the smallest amount denomination left to pay out. But having done that, now you're stuck with using 1-cent coins. If you had thought ahead, a greedy decision would not to have used that largest denomination, but to use two 15-cent coins. But decision trees don't let you look ahead. They make the best decision they can at the time, and then they move down the tree, and they don't look back to see if they could have made a better decision. Decision trees are also sensitive to the particular observations in the training data. Remember, I talked about an 80-20 random split of the training data. A different random 80-20 split would give me different observations, and then that would result potentially in different variables being split at each node. So different choices on the randomness will give you different decision trees. Decision trees often overfit the training data too well versus the test data. And what's the solution on decision trees is multiple trees. And not surprisingly, that's called a forest. And so what you do with decision trees is you run hundreds or thousands of them. The computer doesn't care. Again, nowadays, that's an easy thing to do with all the RAM and CPU you have. So you run thousands of trees with different choices of which observations and which variables get used each time. We're not going to do that, but that's sort of an interesting concept. So this is using the Titanic data. This is my first cut at a decision tree. And so the algorithm does all the work for me, although a few slides from now, you'll see that I made some changes to the algorithm. So the algorithm decided the first way to split the data was by gender, male, female. Then going down this path, it's split by age, then by number of siblings and spouses. And that gets you to the next level, and it decided no more splits made any sense. Going in this direction, it did not split by age, but it split it by fare class, then dollars of fare, and then age, and then that gets you to the bottom. And so now any observation belongs in exactly one of these partitions. Every observation belongs in one of them. There's no observations missing. So if I had a new observation, I would run it through this tree. It would take me to one of these. And then the majority vote of this final node is the prediction. So the majority vote of this one is a 0, which is did not survive. This doesn't mean everyone in this node did not survive, but that's the majority vote. So that's how the decision tree decides what to do with new data. And then I took my test data. Remember, I had 1,300 or so passengers, so I think this is 20% of it. It really doesn't matter how I did with the training data. It's how did I do with the test data. And of course, the test data, I do know who survived and who didn't. And so on my test data, my accuracy down the main diagonal is 96%, which is excellent. This often does not happen, as you might imagine. Down the first row, the true positive rate is 92%. That's also quite good. I've done other data sets where these things are in the 60s, and that's not as good. So this is sort of the default attempt. But I do have some things I can play with. I can play with how sensitive do I want to make the splitting? How large do I want to make each of these splits to be? How many observations in each of them? And a few other things. So here's another possible decision tree. I realize these things are not readable, but the point is I relaxed some of the assumptions on how many items I wanted in each tree, in each node. And that gave me more nodes and more items down the bottom. But interestingly, that reduced both the accuracy and the true positive rate. And I suspect what happened is I overfit the data. I suppose it was a better fit with the training data, but a lesser fit with the testing data. And that's the issue with decision trees and with other models. It's easy to overfit the training data, but then you come along with different testing data and it doesn't work quite as well. So here's a third attempt. This is not quite as many relaxations of the parameters as the second, but a few more than the first. So I've got a few more nodes. So this is a different different splits than the first one. It's an even better accuracy and true positive rate, I think, than the first one. And 97 and 96 is clearly as good as I'm going to get. Of course, I could play with these forever, but I'd be quite happy with these, and I think so would any client. So now let's talk about regression. And we agreed we're doing logistic regression. So we're calculating the odds ratio, and it's the natural log of the odds ratio. So the ln, the ln odds ratio. And first I'm going to start in the default case with all 7 of my variables. So I'm putting these into a logistic regression model. This is sort of, I think, the standard output of a regression model, although in logistic regression, the columns have a slightly different meaning. This is the coefficient estimate. This is the standard error of the estimate, which relates to the variability of the estimate. This is the z-value of the standard error. In normal linear regression, it's a t-value. I'm sure the statisticians among us know exactly why you don't do a t, but you do a z. I don't know the answer to that. Maybe someone will pipe up later. And then this is the p-value of the z. So this is the probability of getting a z-value as extreme of this. And then the asterisks are various thresholds on the p-value. 0.001, 0.01, 0.05. So these are the coefficients of the regression model. And then there are a few more measures, null deviance, residual deviance, AIC. I'll talk about that in a moment. So this is sort of the default attempt. So these are the variables that sort of suggest have some statistical significance in the regression, and these don't. So now with the regression models, we have many combinations of which variables we want to consider. So I think a reasonable thing to do is let's exclude these variables whose p-values are too high and are not statistically significant. So let's run it again with fewer variables. So this excludes the less statistically significant ones. So these are my new coefficients and my new measures. And now let's think about interpreting the coefficients. In linear regression, the interpretation of the coefficient is it's the marginal change in the dependent variable, holding all other independent variables fixed for a 1 unit increase in that independent variable. It's not exactly the same in logistic regression because we're really calculating the ln odds ratio. So what this coefficient is, it's a for a 1 unit increase in the independent variable, it's the expected change in the ln odds of success, holding all other independent variables fixed. So it's how does the ln odds ratio of success change for each increase in x. And so for the particular variables used, P class is the passenger ticket class. And the regression actually converted these into three variables. This was one variable with three levels. The regression converts it into three variables for regression purposes, three dummy variables, where third is the base. As the class improves, the ln odds of survival increases. And that sort of makes intuitive sense. The people who were in the lowest class of ticket purchase were further away from the main deck. It took them longer to get to the main deck. The effect of being male decreases the odds of survival. The old women and children first. Women survived as a percentage basis better than males. An increase in age decreases the odds of survival, and an increase in the number of siblings or spouses decreases the odds of survival. So this is what you conclude from the regression coefficients. The other measures from the regression model, there's something called AIC. I'm not sure how you pronounce that. May or may not be French. This measures the relative quality of the models, adjusting for number of variables. So this said the second model is slightly better than the first. Residual deviance compares the predicted versus actual. Lower is better. Area under curve, I talked about this briefly earlier. When we consider false positive versus true positive rates, but we vary the probability thresholds. The default probability threshold is 0.5, but there's nothing sacred about that. You can ask for a stricter probability threshold or a less strict. And when you do that, everything changes. If you just plot the, it's called the receiver operating characteristics curve. If you plot the false positives versus true positives and calculate the area under the curve, that's another measure of accuracy. These nines are very good. Also, there's no standard R-square statistic for logistic. Perhaps the statisticians can explain that better than I can. So based on a combination of the trees and the regression, here's the conclusion. Who is most likely to survive? Women over men, younger ages over older, first class over third class. Remember, first is best. Smaller families over large families, perhaps the large families, and there were some huge families in this. Perhaps people did not get into the lifeboat until like all 8 family members were able to have space, and that caused problems in survival. Higher fares over lower fares, although this had a weaker significance. There are a lot of references to the history of the Titanic, including every passenger. The last one died at age 97. She was two months old at the time. This was a classification problem. And for the longest time in my study of statistics, I was not particularly interested in classification problems. And certainly as an actuary, I was interested in predicting dollar things, dollars of claims. But this is a classification problem. classifying a record into a finite number of classes. But this problem of classification turns up in a lot of places. I don't know if FGCU has anything like this, but college admission, you could certainly create a classification problem for students in general or math majors in particular. You could come up with a database with a history of based on the database who was offered admission or who wasn't, who graduated and who wasn't. That would certainly make a fine classification problem. There may or may not be, there may be reasons you might not want to do this, but you certainly could. Loan approval and potential default. We all know about credit scores. Credit scores are a kind of classification. And the use of credit scores as to whether you should be offered a loan or not. Medical diagnosis of a particular disease, particularly for doctors who somehow have to maintain in their heads an enormous database of diseases and diagnostic conditions, spam detection in emails. So these are a lot of ways that classification comes in. I do suggest that you be careful of disparate impact of a protected class. And what does that mean? If you were doing a college admission type thing, you certainly wouldn't use certain kinds of variables. You certainly would not use race as an independent variable to predict admission or graduation. But nevertheless, you may end up having a disproportionate impact on race, not intentionally using race, but because races have a disparate impact of the variables you do use. So I just throw out, be careful of that. This was a free database from the Kaggle dataset, subsidiary of Google. There's just lots of free fun data sets out there to play with. UC Irvine seems to like to do this. For all the baseball fans among us, Sean Lahman spends an inordinate amount of time giving baseball data freely available. I recently calculated win-loss percentages that exceeded 600 on everyone since 1871. Why? Because I'm both a baseball nerd and a math nerd. Lots of other places with data sets. And it's just a fun thing to do. So happy data sciencing. And lastly, I want to leave time for questions, but I do want to say that I became acquainted through FGCU, through the Actuarial Club. I think it's taken a hiatus. I think it's about time to bring it up again. And I hope there's some interested students who will be interested in starting up the Actuarial Club in the fall. So that concludes my remarks, and I'd like to open it up for discussion.
Well, let's first all give Jerry the now common silent Zoom round of applause.
Let me show you. I am wearing my FGCU shirt. I don't know if you can see it.
Oh, yeah, I can see actuarial science. Yes.
Okay.
All right. So, do we have any questions?
Anywhere.
You can certainly put them in the. You can put them in the chat, or feel free to unmute your mic and go ahead and ask.
I'll throw one out then if you don't have one. What would you think about having a database of freshman math majors with the goal of determining, are they going to finish with a math major? Oh, silence on that one.
Might hit a little too close to home. There's a question in the chat. Kara said, is there a good reference you can recommend for getting started with data science?
Do you want a book, or do you want YouTubes, or what?
I mean, I would assume any, in fact, books or, yeah, both.
There's just literally thousands of YouTubes. There's also probably thousands of books. Let me find my favorite.
Well, Jerry's looking for that. Someone in the chat said Data Camp.
My one single favorite is R for Data Science. It's by Hadley Wickham, who is the guru of R. You can certainly learn a lot from this. There's lots of free stuff out there, and there's lots of paid stuff. Coursera, Udemy, offer lots of free stuff. And just search for YouTubes. But it's an enormous subject. I'm this close to my master's in data science, and I think I'm hot stuff, but I know very well how little I know. And it's like someone with a master's in math. I bet they know a lot of math, but I bet there's a lot they don't know as well. But it's fun, I'll tell you that.
We've got another question in the chat. I'll read it out, but you can probably read it as well. Were there any cases in which the tree and regression predictions for a particular parameter differed? And if so, how did you determine which result to conclude with?
I did not study that for this. I don't know.
I just want to make a comment that I think that the, pointing out the messy and missing data, and I mean, you kind of commented on it, like that real data is often not perfect, and we often in textbooks and exercises definitely do not give an impression, right? And so I think it's really interesting to include examples like this where, half of your data set basically didn't have one of the categories, right? I forget what it was. If it was the fair class or something, right? Like that's really interesting that you just kind of have to get rid of it because half of it's missing.
And of course, I'm sure Wayne will agree with me on this. That's pretty typical of insurance and reinsurance data. That the data is often pretty dirty.
Yeah, the other side of that is you have a lot of it. And whether it's pricing, determining who you want to underwrite at what price, how you want to manage accumulation, where you might be overexposed to catastrophes, or want to mathematically determine how much reinsurance you want to buy and what type, or setting reserves for losses that you haven't paid yet, or as Jerry mentioned earlier, you want to identify fraudulent claims, not so much so that you can quickly, promptly pay the legitimate claims. That's what's good for customer relations. Also, the same thing with your underwriting. The more you use analytics to streamline that, the faster you can get quotes out, make your agents happy, customers happy, and so forth. So this is pervasive. And Jerry gave you one very good example, but it just permeates everything in the insurance industry right now. And actuaries bring together the domain knowledge on Jerry's first Venn diagram, and then the analytics and the math. And that's why they're increasingly valuable within an insurance company and as consultants to insurance companies right now, because this is exploding exponentially.
I think it's true that more and more organizations in any field are hiring data scientists, but then that's equally true within insurance companies. There are separate data science departments in insurance companies. There are actuaries who specialize in data science, and it's just an exploding field. And It's more and more of your students, even your good math majors, may find themselves in data science careers.
Well, as an example, the
Having said that,
current the
Yep.
current president of the Casualty Actuarial Society is a woman, and she is with Zurich, and she's not in the actuarial function. She's in the data science department. You know,
I didn't know that. But having said that, FGCU has had a wonderful actuarial club in past years, and unfortunately, it's kind of dried up. But actuarial is a wonderful position, a wonderful profession. I've done embarrassingly well at it as an average actuary, and Wayne and I would really like to encourage your math students to consider an actuarial career. And one of the ways to move that along is to reestablish the actuarial club. So particularly if there are some students either in the live audience or in the Zoom audience, I hope you'll think about restarting the club in the fall. Wayne and I have a lot of ideas to get that moving, but we can't do it without the students.
Well, hopefully the prospect of being able to meet in person will make that even more attractive, right?
yeah.
That things return to normal and we can socialize a little bit. So I see, Kara, you had your hand raised. Is there a question in the room?
Yeah, there was just a conversation in the room about, so since age was a predictor, you said like if you were younger, then you were more likely to survive. And so we had the question that since you replaced, say, 10% of the data by just plugging in, I think, the mean value for the age, would it have been more prudent just to eliminate those passengers from the list and work with 1,800 or so, or 1,700, right, passengers data, and then modeled it that way?
I certainly thought about that. It just seemed like a lot of data to eliminate, and then you're eliminating it for all the variables.
Mm-hmm. Yeah.
But that's certainly debatable, and I'm sure thousands of people have worked on this Titanic data set, and I'm sure no two people have done it the same way.
Yeah, it was interesting. We were debating about whether or not to keep that data, or how do you decide?
And that's among those things that makes data science and actuarial work interesting. These are not fields with a single right answer.
Yeah.
Although most math tests have a single right answer, don't they?
Yeah. It's the arts, right?
Any other questions?
Well, I encourage you to even just explore the data sets that are available. There's a data set for just about anything. Of course, without the computer knowledge or the tools, there's not much you can do with them. But if you have a favorite hobby or interest or something, there's probably a data set on it. I've done really fun things analyzing text, including politically. I've analyzed Hamlet versus an actuarial short story to see how they compare. These are also tools of data analysis. And in fact, Augustus de Morgan, de Morgan's Law, is one of the first well-known mathematicians to apply statistics to text analysis. And he analyzed the writings of Shakespeare in the 1800s.
All right, well, I will welcome you all to, or invite you all, sorry, to thank Jerry again, as some of you have done in the chat, and I'll echo those, and thank you all for attending, whether you're on the Zoom call or in person. And so, as he mentioned, looking for students to restart the Actuarial Science Club. Hopefully some of you are interested in that. And keep an eye out next semester as we think about planning our possibly in-person colloquium series to return in the fall. All right, thanks everyone.
Okay, thank you.
All right.
Yeah.
Thanks again, Jerry.